Boom. Hello and welcome back to Calculus 3, section 12.2. We are talking about functions of multiple variables, and we are going to talk about the graphs, and we are going to talk about the domain, and we're going to talk about level curves. So plenty of topics in this section. So we start first with the function of two variables, and that can be generalized to any amount of input variables that you want. So let's start with the definition. And this is again two variable only, which we extend later on. Does anyone remember that the function is a rule which assigns to each x in the domain a unique y in a range? Yeah, we're going to write the same thing now for Calc 3. So, function z equals f of xy is a rule which assigns to each point xy in the domain a unique z in the range. So if you took pre-calc with me, if you took Calculus 1 with me, you know this definition. And now we replace the input domain x with the input point xy, and that's the point on the floor which will give you a z value somewhere. Now what I need you to see immediately is this rag, right? Can be, if you look at it this way, it's a plane, right? But now when I put it on my hand, it takes the shape, right? Now this function, this surface, right, that wobbles like this, and now you can think about the valleys and hills and mountains. This shape, each point that makes up the surface is the elevation z over the xy location on the xy plane. There? So, there is a location on the floor, and then you draw a normal orthogonal vector up. It's going to hit the ceiling in one point. And that's the z that is produced with the xy input. So now your input is both x and y. And I can again have certain values that are not allowed into our domain. I still have the domain, obviously. That's all of the points x and y that we can plug in. And we have range, which is all of the z's. The mapping over here goes from xy plane. You have some domain over here to a simple z-axis location. And that is, right, this is the range of z. So a point xy is going to give the image. So you have a two-dimensional input which provides one-dimensional output. A very simple example to compute, this is a pre-calc level technically for this. I describe my z as, which is a function of x and y, right, as, let's say, 2x squared minus y plus 1. All right? So you see that you have variable x and variable y, and they produce the z on the other end. So what is z of, let's say, -1 and 6? Well, you just plug in. It's 2 -1 squared minus 6 plus 1. So that's going to be 2, 3, -3. And you see that you are getting a single number output. Now, you can write this as a ordered triplet, which is a 3D point, -1, 6, -3, x, y, z. Right? So we have a triplet, ordered triplet, because it's always x, y, z. And technically that's it. Again, we are going to underline domain, the word unique, the word range, the word rule. So the word rule is what? Is our formula that we have. And when we change the formula, we're changing the rule, which changes the rules of computation, right? And then domain is now this region on x, y. Think of it as a puddle, all right? That example just popped up in my head. So you see, wow, that might be a really good way to explain the domain. So imagine a puddle on the ground, and the only way for you to get wet is to step inside that puddle. If you're standing outside of the puddle, you don't get wet. You don't get wet feet, right? So what is the domain? The domain is going to be the part of the region that it's infinite. In every way, it's infinite, right? It's not just infinite for x and infinite for y. This is on the floor, right? It's infinite forever, ever, 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 ever. Now, the boundary of the puddle creates the domain. And if the function is feet are wet, 1, and feet are not wet, 0, right? The domain of that function, when you are getting wet feet, is when you step inside the puddle. So all of the values inside the puddle will produce the answer. Now, thinking about this domain and you know, other things, f of xy is equal to, let's say, x minus 3 over y plus 8. What's the domain?
What do you say then? All the values inside of the puddle equal the domain?
Yeah, the domain. Because that's where you're getting wet, right? When you step in it. Now, looking at this example, x minus 3 over y plus 8. What is the domain for this? So, I really don't need to graph this. Right? I don't need to graph this. What I need to do is to make sure that I'm not dividing by 0, that the square roots are not taking for negative numbers, right? So that's all I need to worry about. The rest, I don't care, right? The rest is fine. So we definitely need to have y plus 8 not to be 0. Which means y cannot be negative 8. But what does that entail for our domain, right? So if you are to draw this thing, y negative 8 is this line here. -2, -4, -6, -8, right? So that's that. And you can pick any x. So you are not allowed to have in your domain any point in this space, this infinite space, that has the y coordinate as -8. You're allowed to have anything else. So now, you can write your domain as like this. So what is domain? Domain is r squared. Now, this notation, you've seen it before, this notation stands for entire xy plane, which means everything in xy. Imagine this floor, guys, imagine this floor extending infinitely in all directions. That is going to be r squared, right? That's the notation for it. And then we are going to subtract set of all points where y is not allowed to be -8. This is a set of points. Right? Set of points on that line. So we are excluding this line. We are technically cutting. If I am to take a sword and cut, oh, not through this one. This is a work of art. I wrote on it. This exam is unbelievable. I should make copies and everyone should frame this to see what the piece of art is. I just don't, I've never seen anything like this. Never in my educational career.
But you graded my paper.
I did. Look at this. See this? This is absolutely amazing. So we're not cutting this, we're cutting this one. Yes. Yeah, there we go. All right, now we're talking. All right, this one. So y equals -8. I'm going to take a sword and just go like this, right? That cut is going to separate the two, and it's infinite line, because this line y equals -8 for this particular xy surface, which should be on the floor, right? Is that line is going to be separating clearly the bottom cut from the top cut, and that line is where all of the points that are not allowed to be in our set, that's where they all point. That's where they are. So that's that part. So that's the domain. Let's take a look at another example, domain. Say you have your f of xy, again, that's z, right? Equal to, say, square root of x minus y plus 1, right? So you look at this. Well, what do we know about square root? What is not allowed? Negatives, very good. 0 is cool, but negatives are not allowed. So, to find the domain, we're going to say that x minus y plus 1 needs to be bigger or equal than 0. That's the only requirement. And now you work this out. You move y to the other side. You get x plus 1 greater or equal than y. And then you just write it as y less equal than x plus 1. And this is your domain. This is it. Now, can anyone tell me what does this mean? what is the physical domain of this function now that I wrote this? What is the physical domain? What should I draw? What should I either exclude or shade? Yes?
Would it be a diagonal line? X plus 1?
So I am supposed to draw, don't call it diagonal line, just tell it's a line, 45 degrees, going through 1, sure. And then, what now? And I'm going to shade. Now, do I shade above or below? Below. So this part over here, I'm going to change the color. This part over here is the domain. Now, here I am daring you to pick any point from the upper. It's wrong to call it upper half, but let's call it. Pick any Canadian point. Really? See? You can fix every issue. Pick any point in Canada. See what happens with the function in this case, right? So, hopefully, right, naturally you should pick 0, 2, right? that should be common sense to pick because that's clearly in Canada. And as you place 0, 2 here, what happens? X is 0. That's negative 2 plus 1, negative 1 under the root. See? So it doesn't give us the real value as the answer. So you know it's good, right? So what was this? This was my test point. That was my test point, and we saw that it's good. Now plug in 0, 0, which is definitely in US, and you get square root of 1, which is 1. Pick any point in the shaded region. You are going to get a good, you're going to get a value. Stuff that you will definitely see throughout our chapter 13, domain of x squared plus y squared less than, let's say, 9. What would this be? Circle radius 3. All right, I'll give you circle radius 3, but keep talking to me. The inside. See, that was what I was after. Because once you draw the circle, there is the stuff inside the circle and outside of the circle. Remember the puddle? So now we're having that, right? So I'm going to draw the circle. I'm going to put that circle on the xy plane. I'm going to say what it is because it is 3 everywhere. But see, the issue with this is that you are not allowed to include the circumference because there is no equal sign. So you have to use dashed line. So I have to go here in this eraser and use it as the eraser, not as a stroke, because it will erase the entire circle. I just need to make this dashed. That's all I need to do. Make it dashed. Go back to stroke, and then this one. So now, what is the domain? The domain is only inside of the circle. So I shade inside. Pick any point inside, like 0, 0. 0 is less than 9. We're cool. Pick any point outside. You can pick 3, 3 if you want to. You can pick, 4, 0. Whatever you pick of those points, it will clearly not give you a good result. If you pick 4, 0, you get 16 less than 9. Yeah, really? Right? So those are some things that we have to consider. Apparently you can't do that. Okay. Good. So I hope you understand domain. And again, there is no way that I can go through every problem with every function. We have exponential, trigonometric, logarithmic, rational, radical, right? So all of these guys are out there. And it is going to be up to you guys to sit down and work on them. And if you get stuck, you have all of the support necessary to get through it. Whether it's the email, office hours, SI, tutoring, divine intervention, right? Whatever helps. Whatever helps to get these problems done. And now we are going to jump into explaining what I did with the rag. I told you that this rag, which I have now on the palm of my hand, is all wrinkly on top, and that surface is a collection of all z's that are produced by the equation from the domain location xy each point, right? Now, again, book is $200 and something for a reason, right? You see it there. You see the shape suspended on the right picture, right? You see the shape suspended in the air, and you see its domain reflection below. You know how easy it is to do this at home? Just get a $1 flashlight in a dollar store and take an object, turn off the lights in the house, and just turn it on. That's all you need to do. Dim the lights. You don't have to shut them off completely. So you will see the domain with your own eyes. All right? That's the domain. It's whatever shadow is casted on the floor or a surface of the desk, if you want to call that XY. Now, you see that black dot with the coordinates X and a Y. When I give you a formula, Z is a function of XY, you plug in X, you plug in Y, like we did in the first example, you solve for Z. And you have X, Y, and Z, which is of X, Y. You create every value that creates the shape like that. You have another picture underneath with the ellipsoid. You have another one with elliptical paraboloid underneath, where you have your domain, and your domain has a point, and you calculate that point in a function. It gives you how tall the Z value is. It's the same thing that you had in your 2D, right? 2D was easier, right? Because for 2D, when I say y, which is f of x, right, was equal to, let's say, x squared plus 1, and if I want to calculate f of 1, f of 2, it's going to be 2 squared plus 1 is 5. And then I have 2, 5, and then I go and I graph. 1, 2, 1, 2, 3, 4, 5, and I have a point. Well, you couldn't see any of that stuff because it was not on. But, yeah. So this was your 2D, and this was your pre-calc 1. Now in calc 3, we're just going to bump it up a dimension. So Z is going to be f of xy. You have a two-dimensional input now, and you might have your x squared minus y plus 1. There you go. So now your f of, let's say 2, 1, is going to be 2 squared minus 1 plus 1 is 4. So you have 2, 1, 4. Two input values, and the last value is the single output value. So over here, in 2D, split input output. For 3D, split input output. Output is the third value. Third value in the point. So we know the way to calculate this. And then you start solving. Now we get to talk about level curves. So level curves, before I show you any cool things, level curves are simply z traces. So you are using z values. See, a level. Think of the level as you are using the elevator, right? Level 1, level 2, level 3, level 4. So we create these level curves by intersecting your physical object, right, and cut that object with z's. So here is me cutting it: z equals 0, z equal 1, z equal 2, z equal 3, z equal 4, z equal 5, z equal 6, let's say in this case, we can't use because going above the object, right? So what do you get? Think of, oh, come on. There has to be something that is constantly annoying. Really?
Yeah.
Stay there. I have a lot of patience. And I actually have nowhere to be, so if this lecture takes till 10:30 because of this, it's 10:30. Hope you cleared your schedules. Oh yeah. Spend very long time. There we go. So what I'm going to do now with this circle is to make it into a ball. So you make a circle and you make it into a ball. And now what I'm going to do is I'm going to start cutting this. Now I'm going to make this ball stand on the 0, 0, 0. So we have x, y, z, right? And the ball stands on 0, 0, 0. And now I'm going to start cutting. So there's a cut right here with z equals to 1. Cut right here with z equals to 2. And z equals to 3. And z equals to 4. And z equals to 5. And the single point z equals to 6 on top. So what am I doing here? What am I getting? I'm getting circles. Now if I remove the object and keep the circles, when you look from the top, all you're going to see are level curves. A level curve here, a level curve here, a level curve here, and a dot in the middle. That's what you see when you look from the top. The dot is from z equals 6 and z equals 0. Right? So the dot is z equals 6, 0, and z equals 6. And then the first ring over here is z equals 2. Oh, I don't need this ring. So this is z equals to 2. No, z equals 1. Oh, I needed the other one. Z equals 1 and z equals 5. I need this one more ring. Then this ring over here is z equals 2, z equals 4, and the fattest circle is z equals 3, which is the equator, if you want to think of it that way. So those are the level curves. And these level curves are very important to study, let's say, a terrain for maps. And that is one of the examples that I'm going to show now from the textbook. If you know proper way to read the map, See, level curves are going to be very close to each other for very steep surfaces. That should make sense. If the surface is really steep and I'm cutting at 1 and then 2 and then 3 and then 4 and then 5, you can see that the width of this circle here and the width of this circle here are almost the same width. So when you draw the circles like this, they're very, very close to each other. Now if you have a lazy surface like that, and you cut here and you cut here, you see that this circle is much smaller than this circle. So they show like that. On map, level curves, these black lines. Now look, they are far apart over here, telling us gradual slope. Not that much of a slope. But over here, yeah, you can't drive there, off-road. So these ones over here are very steep, and you can see that on the picture. So these level curves are, yes?
Can you explain that again? What do you mean with the curve and then?
Well, see, these lines over here, right?
Mm-hmm.
That line is a level curve. And then this line is a level curve as well. And you see they're far apart. When they're far apart in comparison to these level curves that are very close by, when you have them very close by, it's a very steep slope. When you have them far apart, the slope is small. Now I have more pictures, so it will be clear when you see next set of pictures. This is a hill which I drew, right? And you see that these circles progress, or the ellipses progress at a pretty much steady rate, right? But then, this is a good shape. This is a good shape to study. You see, what is this? This is just a bend, right? You take a piece of paper, you bend it like this, and then you slope it like that, all right? Now look at this shape that I'm holding, which is the same as the gray shape over there. Would you all agree that it would be very easy to drive and hike on the top going up? This way. This is still inclined, but if you're walking on this edge up, which is on our picture walking up, it's easy. But now, if I rotate the shape, how easy is it to climb the sides? Right? They are nearly vertical, right? Now look at the level curves. You have your walk on the top. Is this walk along the y-axis? You see the level curves are far apart, telling us that this is not too much of a slope. You can drive, you can hike, you can do whatever you want. But then these sides corresponding here, they're really close by, meaning steep. So when their level curves are clumped together, you have a very steep slope. When they are far apart, the slope is much less. Easy to drive, easy to walk, easy to do all of these things. Now that one. Where's the termite nest? There it is. All right. This is also electric potential function, but termite nest. All right. So, look at that. You can walk anywhere around it without any effort. Go ahead, climb up. So you can see that there's going to be an issue, right? It's an issue to go up this way. And on the picture, that's all of these lines that are clumped together, right? So the two tubes, because you cut at 1 and you cut at 2 and you cut at 3, right? There's just so little differential between them, right? And they create all of these circles, concentric circles that are really, really close. But then over here, right, around, look at that. Big separation of level curves, meaning that the ground is flat and barely sloped and things like that. So this is something that I really can't teach much. You have to sit, you have to observe, you have to go and homework assignment and match your shapes to your level curves. There they are. Unfortunately, the high IQ over here in formatting this. You have 4 shapes over here, and then additional 2 shapes on the next page. I hope this is on the insert of the book in the middle, so you can actually see all of them at the same time, at least that. So 4 and 2 is 6, and then you have 6 level curves.
No, they're on a separate page.
Like when you flip? Oh, yeah. No, they're not, actually. This is the outside of the page, and this is the right page. So when you open the book, you will be able to see them all. Okay. But again, if you're using the online. Now, online homework is going to have this, and then you go to the study plan and hunt as many of these as you can. Because, guys, level curves, your experience is next to 0, right? But you have to be able to do that, right? So practice this visual. Let me ask you this F object, the paraboloid on the right. Which one?
Go back.
Yeah, I would vote for F. So F goes with F, or maybe D. Maybe D. How about E? So A, very good. Observe that the y-axis is cutting big peak, small peak. So y-axis is cutting through them. You see how y-axis is cutting over here through the shapes? Mm-hmm. And it's cutting from negative infinity on y, which is this one on the bottom, because it has a lot of lines, and then the lazy hill over here, right, with less lines. Over here, this shape is backwards. C is backwards. So definitely E and A go together. So I'm just trying to make this so you can actually stare at it and just pick those axes. So Z is completely irrelevant because the level curves give you Z. So I hope you see the way the y-axis cuts through the shape. It goes to the big peak first and small peak. Big peak has to have a lot of lines. It's very steep. And the small peak is not as steep, not as tall. So it's going to rise slower, has less level curves. Now stare at B. You all have that image burnt into your retinas? Because I'm going to go back a page and ask you. A. A. Definitely A. Very good. So please practice more, and you should be masters of this. Matching surfaces with the functions. Here is the A, B, C, D, and capital A, B, C, D. This is where you use the trace. But then there's the issue, oh, there's a cosine, there's ln. Yeah, right, because they are functions, so be nice, right? Don't discriminate. Gotta know for all of them, right? This only comes with practice. And the more problems you find, and remember the study plan. So your homework assignment, right, book has 1 problem each, 4 shapes, 6 shapes. And then your homework assignment will have one of these to pick, obviously, each. But then you go to study plan, and you get thousands, right? So hunt this down if you have an issue, because chapter 13 is coming. It's like winter is coming. Actually, in the show, it's already there, so it's quite cold. For us, it's coming. When we get to chapter 14, the winter will be there. But right now, we're still... So that's level curves. Really not much writing to be done. And now, just to define more than two variables. And I'm just going to say, well, keep adding whatever number of variables you want, right? So if we had z is a function of, x and a y, then I can have w to be the function of x, y, z. Right? This is... What would this be? Why? What in a world would need 4 variables? 4 variables means 4-dimensional space, right? But we live in 3D space. So is this useful to us in any?
Yeah. Shows time.
Shows time?
Use it.
Perfect. You see, would you agree that all of you right now have a unique coordinates on this planet in terms of x, y, and z? You are on a 2nd floor, right, currently? And then there's x and a y, which you can superimpose on the grid and get those GPS coordinates where you are. So at 7:08, you have those GPS coordinates. What are those coordinates going to be at 9 p.m. today? They're going to be different, right? So it depends on your input coordinates that you use there as a location, and then this W could be a time. So someone says, oh, it's 7 p.m. He or she is in class, right? So that's that. But I'll give you another example. And that is that this W could be temperature inside an object. So if I have a 3D object like this, I will have a particular spot inside this bottle perfectly described in our 3D space by x, y, and z, and its temperature is going to be, right? Now let me raise the stakes and say, all right, fine, but can we go and say Q is equal to function of x, y, z, t? This is a 5D space. Do we have a use for that in our science? And the answer is, of course, yes, right? Because remember that I have a location, x, y, z, and then I have the time of the day, which is 7 p.m., and then I have the temperature, the Q, right? You see? How many variables can you tag along in a multivariable function and still have a use of it in our everyday dealings? And the answer is as many as necessary. The weather models, I believe, have 22 variables and parameters, talking about the temperature and pressure and location x, y, z, because the weather in Bamberg is going to be different than the weather in Clinton and so on, right? So you are going to spend 3 of the variables just for location, and then you're going to have time, that's the 4th variable, and then the temperature is 5th, and then the pressure, right? And then all other variables that are there in the weather model, and I believe there are 22 of them. And then you run this crazy algorithm on the computer, constantly feeding initial conditions, which is what's out there right now, to predict what's going to be out there in an hour and 2 hours and 3 hours and 7 days. There's obviously coupled differential equations that do that because we are measuring change, but still, these models are calling for whatever amount of input variables. Now remember what I said, the progression from 2D to 3D to 4D to 5D. You are going to have a point xy, and then the split between domain and range, you are going to have the output variable, and then you are going to have x, y, z over here, and you are going to have just one at the end. That is your range, and you have two input values. And then we have x, y, z, w, and you are going to have this one, and then x, y, z, t. It doesn't matter which letters you pick. It doesn't even have to. You can do A, B, C, D, E, F, G and be done, right? So this. Now, when you look at the associated equations, you are going to look at y equal f of x, z equals f of xy, w equals f of xyz, and then in this case q equals function of xyzt. By the way, this thing over here, it's called space-time. You see that? It's just four letters in a pile. Space-time, three-dimensional space, one-dimensional time, and it's mushed together in the same coordinate. I mean, four coordinates, the 4D point. So there you go. That's that. So now, how do I take my definition, which I had in pre-calc 1, in calc 1 also, and then now we have the calc 3 for 2D. So what is the multi, right? So you will see whatever you need, you will just call your point 4D, right, in the domain, or 5D in the domain, or 6D in the domain, creating a single output variable on the other end. So you can have anything. And now my favorite image, boom. What's that?
Cool.
It's cool, right? So, it could be, say, think of a car engine block, right? I mean, the gas-powered cars, obviously not the electric one. They don't have these primitive things. Why are you laughing, man? The car that we have is the technology from not even last millennium, 2 millennia ago, right? They were built in 1800s. We're using the same principle today. We just put a flashier shape, but we are still exploding dead plants and animals to go from point A, point B on a 27% efficiency. This is how pathetic we are as a human species, like collectively, right? Anyway, well, it sums it up, right? So 27% efficiency. So where is the rest? 27% of what you pay for your fuel is taking you from home to school and runs your air conditioning and your music in your car. And where is the rest, 73%? Yeah, it's the heat and it's the friction and it's, shaking and the noise, all right? And the exhaust gases. That's where you're 72, 73, 75%, depending on the car. So anytime you pay for the gas, it's that 75% of the money goes directly into garbage, and 25% of your money gets you from point A to point B. That's what you're driving right now, and that's why you should buy a Tesla tomorrow if you can. So there's a distribution of heat. The redder it is, the hotter it is, the bluer it is, the colder it is. Now you all understand that this shape is governed by f of x, y, z, and then the fourth variable floating around is hot, cold. That's the fourth variable. So you have a four-dimensional. So I can write the formula for this particular thing here, temperature in x, y, z, right? Sorry. Temperature as a function of the location. Temperature as a function of the location. That's what I meant. So it's a 4D space because you have 1, 2, 3 input variables, and the temperature is the fourth variable right there. Again, you can link more variables for more complicated models if you need them to. And then there's your homework. Ta-da!